Welcome all. Today we are going to talk about material characterization using XRD technique. Let's begin with a quote. We don't meet people by accident. They are meant to cross our path for a reason. This is a very interesting quote since I have come here for a reason to share with you how XRD is a very fine tool for material characterization, and there is a lot of new horizons of opportunities of wisely using this technique in materials science research. The talk is divided into two parts. One is diffraction basics, another is we will discuss about recent research activities in X-ray diffraction. We will begin with part 1, diffraction basics. First of all, before going into the basics of diffraction, I want to quote a story about how a square met circle in a novel written by E.A. About. The novel's name is Flatland. Square lives in a two-dimensional world, and Square one time encounters Spear, who is a popular guy in three-dimensional world. So in three-dimension things are different, and Square was a cube in three-dimension, and Square was not able to understand what is happening with him. So the Spear advises Square, saying that distress not yourself if you cannot at first understand the deeper mysteries of spaceland. By degree, they will dawn upon you. Now, the phenomena of diffraction was documented in 1665 by Italian Francesco Maria Grimaldi. He was concerned about the waves in a pond and how they superposed and how they interfered with each other. Here you can see a photograph of a duck moving in a wave in a pond. There is a planar wavefront which is touching this duck, which is the obstacle, and then the wave changes into circular wavefront. Now, there are some theories in superposition and interference. When multiple waves pass through the same place, the total wave is obtained by adding together the individual wave displacement. This is called the principle of superposition. When two waves which are in phase, that is when the crest and crest comes together, trough and trough comes together, there is a bigger wave, that is called the constructive interference. And when the trough and crest comes together, it becomes destructive interference. This can be demonstrated by a laser double slit experiment. If the diffracted light is projected onto a screen some distance away, then interference between the light wave creates a distinct pattern called the diffraction pattern on the screen. And when we look into the pattern, we see the reciprocal nature. The relationship can be seen in the diffraction pattern of the slit. Small features of the diffracting object give wide spacing in the diffraction pattern. And if we clip more complicated mask, for example a periodic row of apertures, then more intricate diffraction patterns result. But still, the same basic inverse relationship follows. Now, to understand the diffraction pattern, we need to get an idea about reciprocal lattice. What is a reciprocal lattice? Reciprocal lattice was envisaged to represent planes. First of all, let me tell you that this representation is better than normals. A reciprocal lattice is a projection which displays both orientation and interplanar spacing. Normal only gives direction, but in this case, we get both orientation and interplanar spacing. How is this done? There is a procedure of doing or mapping the points in reciprocal lattice. Let me share that points with you. First one, you draw a normal to each crystal plane from a common origin. Set the length of each normal equal to or 2 pi times the reciprocal of interplanar spacing. Mark a point at the end of each normal which represents the crystal plane. And by these three procedures, we get a collection of points. A collection of points obtained in this way, corresponding to various planes from a lattice array, is called reciprocal lattice, and whose lattice point direction gives the orientation of plane and distance of the point gives the interplanar spacing of the plane. So let us have an animation showing how a real space is mapped into reciprocal lattice. Consider some equally spaced lattice points in real space, and then you choose an origin, and then you define one zero plane. What you have to do is that you draw a normal to that plane, and the normal touches that plane. Here it is shown as line because we are drawing it in a two-dimensional surface at a distance a. Now find the reciprocal of that a, multiply by 2 pi, and you call it as a star. And in the same direction, in an altogether different space, we call it as reciprocal space, we mark a point as 1, 0. 1, 0 is actually a plane, but it is marked as a point in reciprocal space. Similarly, you mark the next plane as 0, 1, and then you draw a normal. That distance you can call it as b. Then you find b star and mark it as 0, 1. Likewise, we can continue marking all the planes 1, 1, 2, 1, etc. And what you have to do? You have to draw a normal to that plane, find that distance, take the inverse of that distance, multiply by 2 pi, and then you can mark that plane. This can be continued. This is called the reciprocal space. So what is happening is that when an X-ray is impinging on the sample can be called as a slit. Then the X-rays get diffracted and we get a pattern in space as shown in the figure. And that pattern is actually the reciprocal lattice representation of the slit. So some of the properties of the reciprocal lattice is that the diffraction pattern of the crystal is actually the map of reciprocal lattice of crystal. And if the crystal is made to rotate, both direct and reciprocal lattice rotate. The primitive vectors of the direct lattice have the dimension of length while those of reciprocal lattice have the dimension of length raised to minus 1. Now let us talk about some history of how X-ray diffraction evolved. Everything started in 1901 when Röntgen discovered X-rays. The Nobel Prize in Physics 1901 was given in recognition of the extraordinary services he has rendered by discovering of the remarkable rays subsequently named after him. You can see a photograph where you can see it was the first X-ray. It was actually taken and it is the X-ray of Röntgen's wife, and you can see the wedding ring in the finger. Now the second important person whom we have to discuss is Moseley. Moseley was able to show that the frequency of certain characteristic X-rays emitted from chemical elements are proportional to square of number which was close to the element's atomic number. Moseley died at a very early age. He died at 27. And if you look into the Wikipedia, you can see that when the World War I broke out in Western Europe, Mosley left his work at the University of Oxford for Royal Engineers of British Army. Mosley was assigned to the force of British Empire soldiers that invaded the region of Gallipoli, Turkey, in April 1915 as a telecommunication officer. And Mosley was shot and killed during the Battle of Gallipoli in 10th August 1915 at the age of 27. And experts speculate that Mosley could have been awarded the Nobel Prize in Physics in 1916 had not he been killed. And that is why still we can find that 1916 Nobel Prize in Physics was never awarded. He found a very interesting relation that the frequency of X-ray emitted from an element is proportional to Z minus 1 whole square, or it is proportional to atomic numbers square. And the next person whom we have to discuss in diffraction is none other than Low, Max Theodor Felix von Low. He is a German physicist who won the Nobel Prize in Physics in 1914 for his discovery of diffraction of X-rays by crystals. That method is called the Low's method, and he has devised an equation through which we can describe how diffraction has happened. That is, A into n is equal to h lambda, B into n is equal to k lambda, C into n is equal to n lambda. And the crystalline materials are characterized by orderly periodic arrangement of atoms. Diffraction occurs when each object in the periodic array scatters radiation coherently, producing constructive interference at specific angles. The diffraction from different planes of atoms produce a diffraction pattern which contains information about the atomic arrangements within the crystal. And continuing, we can have another equation called Bragg's law, that is equal to n lambda is equal to 2 d sine theta. Constructive interference occurs only when at certain theta angles corresponding to certain h scale planes, when specifically the path difference is equal to n lambda, when lambda is wavelength. And Bragg has once said that the important thing in science is not so much to obtain new facts as to discover new ways of thinking about them. And he devised some of the conditions of observing X-ray intensities for cubic crystal. For simple cubic, all the reflections in all the HKL values are allowed. While for FCC, when HKL is either even or odd, then only we will get a reflection intensity. But for BCC, when H plus K plus L is even, we will get reflection intensity. And in such a way that X-ray is a very fine tool to distinguish between simple cubic, VCC, FCC, different types of lattice in cubic structure. Now, this idea that 2D sin theta is equal to n lambda was actually postulated by a father and a son. This one, William Henry Bragg and William Lawrence Bragg. They were British physicists and chemists who uniquely share the Nobel Prize in Physics in 1915. Another person in this important person who we have to discuss in next diffraction is Rosalind Franklin. Nature has described that Rosalind Franklin's XRD are among the most beautiful X-ray photographs of any substance ever taken. She is associated with Watson, Crick, and Wilkins in the construction of double helical structure of DNA. Even though Watson didn't mention her name in the discovery, later it was found that it was Rosalind's work. Probably that is why the reason when the Nobel Prize was awarded in 1962, there was a film released in James Bond series as Dr. No, where the villain has a resemblance with James D. Watson. And actually, when I have to make a point that Nobel Prize is not the ultimate aim in the life, there are persons who has contributed much but was never acknowledged by Nobel Prize. One such person is S.N. Bose. S.N. Bose, together with Einstein, has postulated new area of statistics as well as postulated bosons, talked about polarization, talked about spin, and many other things. While Fermi and Dirac also talked about the same thing, Einstein, Fermi, and Dirac got Nobel Prize in 1921, 1938, and 1933. But Satyendranath Bose was never acknowledged. It's interesting that three of the four people involved in the development of quantum statistics won Nobel Prize, and only Bose failed to get it. Not that he was never nominated, he was in fact nominated many times, but Nobel Committee failed to honor him. This happens at times, and the classical case is that of Mahatma Gandhi, who was consistently overlooked for the Nobel Prize for Peace. Of course, Gandhi was far above the prize, but this shows that how those who give awards are sometimes blind. One day, an interviewer asked, "Boss, are you sad about it? Let me read that incident for you." Years later, Bohr discussed about how he derived Planck's radiation law more convincingly than Planck himself in his paper. He said that a factor of 2 was introduced since photon carried 1 unit angular momentum, which would take 2 orientation, which is later called spin states 1 minus 1. But Einstein was since satisfied with that. The old man crossed the portion saying that it wasn't necessary at this stage to introduce such a concept. In those days, it didn't make any sense. But now, it has a meaning called polarization. The interviewer asked Bose if, after the discovery of the concept of spin, had he tried writing to Einstein claiming the priority in the discovery of spin of photon. An amused Bose replied, "But how does it matter who proposed it first? It has been found, isn't it?" So, that is the story of Satyendra Bose. So, whatever is being found, it will be actually useful for science. One of the interesting contributions of XRD in popular culture I would like to share. 7-Up is a brand of lemon lime flavored non-caffeinated soft drink. 7-Up has been reformulated several times since its launch in 1929. In 2006, the version of the product sold in US was reformulated so that it could be marketed be 100% natural. Behind name, lithium contained in the original recipe, which has an atomic mass of approximately 7. It has been said that lithium in the original drink raised the overall pH of the drink above pH 7 depending on how liberally lithium drug had been added. So, the original 7-Up was a mind-altering substance. According to citrus soft drinks, it is packed with mood-enhancing lithium. So, now lower doses are quite good that it can lower the rates of suicide, murder, rape, etc. It's been found like that. So, this presence can be detected using XRD. As well as the art forgery can be also found out using XRD. Art forgery is creating and selling of art which is falsely credited to other. Usually, more famous artists can be extremely lucrative, but modern analysis techniques like XRDSM have made identification of forged artwork much simpler. Now, let us go to part number 2, where I'm going to talk about some recent research activities involved with XRD. I am right now working in Kerala University. We have a very good facility, Broker D8 advanced facility in our university, which is open for all with a minimum payment. You can access all the facility in our department. And these are the faculty members. I will begin with a quote by Richard Feynman. XRD finds a nice application in nanotechnology. The principle of physics, as far as I can see, do not speak against possibility of maneuvering things atom by atom. So this small world, the nanotechnology has been the ultimate toy box of nature, of atoms and molecules. The possibility to create new things are appearing to be limitless. And Stromer also believes that there could be a better world using nanotechnology. And IBM has now created graphene transistors, which has a very high operating speed of 100 gigahertz. Means that they can switch on and off 100 billion times each second, which is 10 times faster than the silicon transistors. So this utopian world can be found, can be restructured, can be enhanced by properly using XRD technique. If you look into the evolution of human, it has started from the Stone Age to Bronze Age to Iron Age. Now we are living in the age of artificial intelligence. Lot of innovative technology has emerged from radio, rocket science, MRI, laptop, internet, laser, etc. So we can say that scientist invents future. So from the ages of where steam engines were, we have moved on to electricity and magnetism, to internet, and now in the age of nanotechnology. It is called the next generation utopian revolution. We are going to master atoms. Nanotechnology will give us to manipulate atoms, resulting in super strong, super light, amazing electrical and magnetic properties. One of the crazy ideas what we can share with you is a space elevator. A space elevator can reduce the cost of space mission by 90%. It is nothing but a 36,000 kilometer extending cable made out of graphene. It is a theoretical possibility, but still we are not able to reinforce graphene to such large extents, but it is theoretical possibilities there. Richard Ernest Malley is a professor of chemistry and physics in Rice University. Along with Robert Kerr, was awarded Nobel Prize for the discovery of buckyballs. And he says the grandest dream of nanotechnology is to be able to build with atoms as the building blocks. And the computer has become mini size, of the size of bacteria, and which is as powerful as a desktop. Whatever I told is not an exaggeration. Countries like USA, Russia, China, India have taken it very seriously. And nanotech activity has been allocated a lot of funds. And here is the graph showing who are investing in nanotech activity. And we all know Moore's law. In every 10 years, the processing power doubles. And as the processing power doubles, this is actually an attribute of nanotechnology. Why we invest like this? Because if you see the day on the first day when man landed on moon, we only had uh, a processing power, an iPhone with NASA. And now with the enhancement of nanotechnology, the same total processing power of NASA is right now with a common man. And nanotechnology has the potential to enhance human performance, to bring sustainable development for materials, water, energy, food, and to protect against unknown bacteria, virus. So nanotechnology can create a machine that only God can build, a machine that can create anything out of almost nothing. So this is a quantum world. And when we talk about quantum world, we should quote Richard Feynman. Once he was asked, how small can you make a machine? He said there is a plenty of room at bottom. Machine made up of individual atoms were possible, but new laws of physics would make them difficult but not impossible to create. What are the new laws of physics? There are some common sense laws of physics like Newton's law, which doesn't fit into the quantum world. If you see the film Honey, I Shrunk the Kids, you can see that in reality, raindrops can be large or greater than ant. They form huge hemisphere due to surface tension, and they act as net that holds water. So if you make an ant 10 times bigger, the volume will be increased by 1000 times, while the area of the leg is increased only by 100 times. And that is ant becomes 10 times weaker than the original ant. So such films like King Kong that terrorized New York City would crumble if you tried to climb Empire State Building if you follow the above physics correctly. And if you see the film The Incredible Shrinking Man, we understand that new tools are necessary to study their effects. So let me share with you some of the interesting developments in IBM Almaden Research Center. Here we have made an atomic abacus. We call it as MEMS, microelectrochemical mechanical systems. It's a technology of very small devices. It emerges at the nanoscale to form NEMS, nano electromechanical systems. MEMS are made up of components between 1 to 1000 micrometers in size. They usually consist of a central processing unit that processes data and several components that interact outside, such as micro sensors. This finds large applications in ink cartridges, airbags, gyroscopes in planes and cars. And these tiny MEMS, which detect sudden braking, creates the electrical discharge, chemical explosion, bills of nitrogen with 1 by 25th of second. It has already saved thousands of lives. But although the nanotechnology is still in its infancy, it has already generated a large booming commercial industry in chemical coating materials. By spraying thin layer of chemicals onto commercial products, one can make it more resistant to rust and change its optical properties. And one such is the enhanced computer screen, stronger metal cutting tools, and scratch resistant coatings. In this situation, I had to talk about Dan Sketchman, and he's a professor in material science, and he has been awarded Nobel Prize in Chemistry in 2011 for discovering a new phase, a new field of quasi-periodic crystals. What is a quasi-periodic crystals? We all know that crystals don't have five-fold symmetry. Whenever we arrange unit cells with five-fold symmetry, we will always find vacant spaces in between such arrangements. Hence, cohesive crystals was not a possibility. But Roger Penrose had already shown through his diagrams, Penrose diagrams, that there could be a possibility of arranging with two tiles to get five-fold symmetry. You can see this figure. So when you use these tiles, which are called kite, and we can see that this actually fits in kite and dart. This actually fits in and forms five-fold symmetry. These type of quasi-crystals are now finding applications in making glass coatings, which are showing various properties with electrical and magnetic fields. So these things are being used for field recognition, person recognition, cocktail party, and even this type of contact lens can be used by students for examinations. We can talk to foreigners. When we talk to them, then this system will give subtitles, and also we can have augmented reality using such type of new materials. And now when we talk about the Argonne National Laboratory, here is the aerial way of Argonne National Laboratory. Argonne has a IBM Blue Gene Q computer, which has a very high capacity processing power. It's actually a byproduct of nanotech. And in this center itself, titanium oxide nanoparticles was used to bind to any antibodies which naturally seek out cancer cells. And it is found that 80% of cancer cells are destroyed using titanium oxide nanoparticles. When we talk about these things, we feel that why we should bother about these things. You see, a person who is suffering from cancer, there's a horrific side of chemotherapy. And they will never say, if you know that, we will never say that, I don't care about that. There is anemia, appetite change, bleeding problem, constipation, diarrhea, hair loss, infection, memory changes, mouth and throat changes, nausea, vomiting, nerve changes, pain, etc. So the right dose of humor, chemo sees innocent through cancer. We have seen such newspaper cuttings also. So this nanotech will be very useful in the future also. And there are some shape shifting situations like we have seen T-1000 perfect killing machine in Terminator. It will be dramatic if we are able to manipulate atom by atom. In future, we know that the fruits of nano will be everywhere, hidden from the view. Sophisticated versions of LCD, LED screens will display around, and regulating electric current flowing through this liquid crystal. One can create colors, shapes on the screen with a push-up button. And Intel scientists visualizing it by creating an computer chip in the shape of tiny grain of sand. And these are small grains of sand which allows you to change static changes on the surface so that these grains can attract and repel each other. And these grains are called sea atoms. And Jason Campbell, an advanced researcher, says that I think of a mobile device and my cell phone is too big to fit completely into my pocket and too small for my fingers. So more, if I want to watch a movie or email, that things are more difficult. So he is coming with sea atoms. Sea atoms are nothing but 200 to 300 million sea atom shaped devices, and they will have profound effects. The first sea atoms will be visualized in toys, and it can be programmed to change shapes by inserting new softwares inside the toy, reprogram it, and entirely a new toy appears. And it can be also used in furnitures where cabinets and newly furnished utensils for requirements in kitchen. You may have also seen Ravan, which is an idea coming from sea atoms. So this cut down the waste disposal, and you don't want to throw out unwanted things again. You have to just reprogram it. But what are the problems? Why it is not happening right now? Because of the bandwidth problem. Nobel laureate Richard Smalley says that can molecular nanobots be built through simple rearrangement? He says no. Much like you cannot make a boy and a girl fall in love with each other by simply pushing them together, you cannot make more precise chemistry occur as desired between two molecular objects with simple mechanical motion. So chemistry is like love, more subtle than that. Now let me talk about my research in Department of Physics. I work on salt oxide fuel cell power, and I am working just because it is much more important topic than we discussed terrorism. So in some reports which we have seen very lately, we see that the fuel cells are the need for the future because it has a security of supply, it has environmental impact, and also it is economically competitive. And the energy demands are not going to diminish any day sooner. So using fuel cells, there is a technology called cogeneration because we can use any type of fuel and clump it into fuel cell, and also this heat can be wisely used. We will get a total efficiency of 88% in fuel cells. And many newspapers are reporting that fuel cells are the hope for the future, and there are more allocation of funds for fuel cells, and solid oxide fuel cells become a solution for all energy problems. And this is one way to fight climate change too. So I will talk a little bit basics about my fuel cell research and what are the latest developments in these slides. A fuel cell is consisting of two electrodes and sandwich an electrolyte that pass specialized material or ions through these electrodes. And solid oxide fuel cell is a device that converts gaseous fuels via an electrochemical process directly into electricity. And air is supplied to the cathode at one end, and we can have anode which will have the fuel, and this works in a simple reaction that H2 plus O2 minus gives H2O plus 2 electrons. And the real dimension of solid oxide fuel cells is very thin, it comes to 1 millimeter. We can stack 30 fuel cells in one stack, and still it is very handy. So we can say that solid oxide fuel cell is highly modular. So modularity is one property of solid oxide fuel cells. Solid oxide fuel cells are also 80% efficient, making them the most efficient fuel cell currently being developed. And there is a fuel flexibility that it can work on various types of fuel. I have just shown that it not only works on hydrogen, it also works with methane. So such possibility is there. And a comparison with other fossil fuel plant, we can see that even if we use methane, we will still have pollution free or very pollution less fuel cell, that is solid oxide fuel cell. If we compare the working for 1650 megawatt operation of fuel cells, and the running cost is very low compared to anything else. We can have 1 liter hydrogen, it can work about 560 kilometers, and people are developing new gen cars for solid oxide fuel cells. And if you work this on fuel cells, we have a very high expectancy of 40,000 to 80,000 hours, which is never expected out of any Carnot engine vehicle. And why fuel cells are not seen right now is because it is a disruptive technology. It is a word coming from a book written by Clayton called as Inverted Dilemma. What is disruptive technologies are ideas or products which have no measurable market right now, but have the potential to become mainstream in a time sooner. So some of the examples of disruptive technologies are like mobile phone, airplanes, electricity, full body CT scan, PC, etc. So since solid oxide fuel cell power has very large force, it has only right now applications in where we can afford large amount of money like airport, medical clinics, hospitals, manufacturing units, etc. So we idea is to how to bring to this to common man. So what are the troubles we are in? Like the electrical resistivity of this solid oxide electrolyte is still high. We have a conductivity of 0.1 Siemens per centimeter, but it is still to be improved. And actually, you may have seen the schematics, and we no need electronic transfer. So electronic transfer should be minimized, and the electrolyte domain can be enhanced using nanotechnology, nano fabrication tools. And chemical constraints are also there. The electrolyte must be stable with respect to electrode materials, oxygen, and fuel gas. And there are also thermal constraints like phase stability and good match of thermal and coefficients with the other components. And also factor toughness, gas tightness, etc. have to be also considered. These are the troubles we are facing. And all these troubles are hanging on a single ceiling, that is high temperature operation of fuel cells, which is operating at 1000 degrees Celsius. So we are doing on research in these lines. Department of Physics is also working on it. There are many other departments working all around on fuel cells, and we are not actually alone. Or actually, we have to admit that we are also far behind. But we are the one who should work on this line because there are 730 million people still relying on biomass in India. So, like Lord the squirrel, we are also helping Lord Rama to build a bridge. So I want to quote Vikram Sarabhai's quote that we are convinced that if we are to play a meaningful role nationally in the community of nations, we must be second to none in the application of advanced technology to real problems of man and society. So this is the actual stacking of a fuel cell. Uh, that you can see electrolyte which comes in the thickness of 10 micrometer. And this emergence of nanotechnology in the recent decades have given a lot of insight on how to improve the electrolyte properties. What all hinderings are there in the electrolyte property can be enhanced using perovskite pyroclostructures. And this has some figures showing how the grain size varies when we prepare through nanotechnology, nanosynthesis methods, and at different annealing temperature we get different grain size. And you are all welcome to visit uh, my YouTube channel where I have given detailed analysis on how to use XRD, how to use X-ray tools like Topaz 4.2 and Diffract suits. You can visit that. Since this is a small lecture, I cannot right now include all those aspects, but you can find that in my YouTube channel. You have to just search Illuminati Physics. So in parting words, we can say that hydrogen cars are going to hit our roads soon. And I feel that we see most of us engage in physics not for making money, but not because we fear, not because we want to power, but the sheer joy of discovery and innovation. That is why we often pass this lucrative job and we pursue a dream not for the dollar. An artist and intellect feels the same. So the goal is not to amass wealth, but to be creative and ennoble the human spirit. I thank you all for patiently listening. You can email to me, you can message to me regarding your doubts, and I am open to discussion. I thank you all for patiently listening. Thank you once again.